Have you ever considered the invisible architectures that make our most complex machine learning models hum with efficiency?
Hmm.
We're talking about the hidden efficiencies within the incredibly complex machine learning models that power so much of our world.
Yeah, the stuff under the hood.
Exactly. How do we make these powerful AI systems even faster, leaner, and more adaptable?
Especially when they're deployed on devices with, incredibly limited resources.
Right. And what if we could automate the discovery of these efficiencies?
Instead of relying on painstaking, often manual handcrafting every single time.
Precisely. Well, today, you are joining us for a deep dive into a groundbreaking paper that directly confronts these pivotal questions.
Okay.
It's titled Kaleidoscope, an efficient, learnable representation for all structured linear maps.
Right, the Kaleidoscope paper by Tridao and colleagues.
That's the one. Authored by Tridao, Nimit S. Sohoni, Albert Gu, and their esteemed colleagues from Stanford, Cornell, and the University of Buffalo. Published back on January 6, 2021.
A really influential piece of work.
Absolutely. Our mission today, for you, our curious listener, with a solid, expert-level grasp of machine learning, data science, and mathematics, is to extract the very core insights and the most surprising, paradigm-shifting facts from this paper.
Get right to the heart of it.
We're going to provide you with a professional, comprehensive overview of kaleidoscope matrices, what they are, the intricate theoretical underpinnings that make them so powerful, and crucially, their practical implications across diverse applications.
Okay.
Our aim is for you to gain a rapid yet thorough understanding of this cutting-edge advancement without getting bogged down in unnecessary detail.
Through the noise.
We're cutting through the complexity to get right to the profound implications that truly matter.
And if we connect this to the bigger picture, what's truly noteworthy here is the fundamental problem this paper addresses.
Okay.
For years, machine learning practitioners have faced an incredibly laborious and, well, often frustrating challenge, manually selecting, designing, and then painstakingly tuning specific structured linear transformations within their neural networks.
All for efficiency.
All in pursuit of efficiency goals, exactly. Think about it. You're trying to optimize for speed, for memory footprint, and for predictive accuracy simultaneously.
A tricky balancing act.
It really is. And each choice is an intricate dance of trade-offs.
Right.
This paper offers a profound aspiration to provide a truly universal, fully differentiable, and completely learnable solution.
The holy grail, almost.
You could say that. A solution that could fundamentally change how we approach model efficiency, moving us dramatically away from that often heuristic-driven manual trial and error process.
Which has been a bottleneck for a long time.
A bottleneck in deploying high-performance AI, absolutely.
So let's truly unpack this problem. It starts with a foundational understanding. Structured linear maps aren't just theory.
No, not at all.
They are absolutely fundamental and ubiquitous components in modern machine learning.
Critical ingredients.
In fact, they are critical ingredients in almost every deployed system you interact with daily, often without even realizing it.
Indeed, their importance goes far beyond just being fundamental. They are, in essence, the very bedrock for achieving efficiency in machine learning models.
Right. Efficiency.
When we talk about drastically reducing computation and memory usage, which is paramount for deploying powerful AI in resource-constrained environments.
Like phones, sensors.
Exactly. Mobile phones, smart sensors, IoT devices. These structured maps are absolutely key.
They're the tools.
They are the mathematical tools that enable algorithms to run significantly faster and models to require substantially fewer parameters.
Which directly impacts energy consumption, real-world use.
Precisely. Energy consumption and real-world applicability.
Can you give some concrete examples of these structured linear maps that the paper highlights? Maybe some that our listeners might already be intimately familiar with?
Certainly. The paper points to a rich variety. On one hand, we have the fixed, highly specialized transforms, like the discrete Fourier transform, DFT, and the Hadamard transform, classic workhorses in signal processing.
Audio compression, telecom.
Essential for all that, yeah. Then, of course, there are convolutions.
The backbone of deep learning.
The very backbone, driving breakthroughs in models that process images, understand natural language, analyze speech.
Ubiquitous.
And finally, we have specialized forms like low-rank and sparse matrices.
Like for compactness.
Absolutely essential for compact storage and faster inference, particularly on those edge devices we mentioned. The role of structure and especially the intelligent use of sparsity, has been at the forefront of recent advances, critical for on-device inference, energy-efficient models.
So it's clear they're indispensable, a powerful toolkit.
Definitely.
But then, as you alluded to, there's a significant dilemma, a major friction point.
Yes.
What's the current predicament that practitioners face when they actually try to use these tools?
Well, this raises a profoundly important question. If these tools are so powerful, why isn't their adoption more seamless?
Good question.
The current predicament is that machine learning practitioners are forced to handpick specific classes of structured linear maps for each unique application.
Like finding the right wrench.
Exactly like that. Imagine a huge toolkit, thousands of specialized wrenches. For every new bolt, you have to try loads out, figure out the best fit, fine-tune it.
That sounds painful.
It is. That's why it's described as a difficult and labor-intensive task.
Okay, why so difficult?
Several factors. First, there's a plethora of classes. Low rank, sparse, convolutions, fixed transforms, you name it.
Right.
Each class has its own unique representation, its own algorithms, specific implementations.
And trade-offs.
Critically, distinct trade-offs in speed, training time, accuracy. What works for images might be awful for language. Furthermore, the conventional wisdom in the field has long held that no one class works uniformly well across all applications.
No silver bullet.
No silver bullet. This diversity means practitioners are constantly stuck in this bottleneck-inducing process. It needs domain expertise, endless experimentation.
A real drag on
A
development.
fundamental challenge, slowing things down and limiting adoption.
That sounds like an immense burden. Surely limits innovation, deployment velocity.
It does.
So in response, the paper proposes a clear set of ideal criteria, a desiderata for what a universal representation should achieve.
Yes, they lay out what's needed.
What are these non-negotiable criteria?
The authors, keenly aware of this burden, lay out 3 absolutely critical criteria for an ideal universal representation.
Okay, number 1.
The first is expressiveness and tightness. It's not just about representing some structures.
Needs to capture the important ones.
Exactly, all important classes. And, crucially, with a nearly tight parameter count, minimal memory footprint, close to optimal,
And runtime.
and near optimal runtime for matrix vector multiplication, as fast as theoretically possible.
Got it. Example.
Well, the DFT has an incredibly efficient ON log n representation,
Right.
but a low-rank transform, say size up to N2, can't tightly approximate it.
So existing methods fall short sometimes.
Often fail to capture diverse structures with optimal efficiency across the board.
Okay, criterion number 2.
Second is differentiability, absolutely paramount for learnability in modern ML.
Needs gradient updates.
The parameterization must be fully differentiable, so parameters can be updated using gradient-based optimization, like backprop.
So it can be learned end to end.
Exactly. Enables it to be used as a simple drop-in replacement for manually engineered components.
Makes sense. And this is where sparsity gets tricky.
Yes. And here's where the paper highlights a significant challenge. Unstructured sparsity while linked to efficient maps.
Like Dessalles showed.
Right. But learning optimal sparse factorizations means finding discrete, non-differentiable patterns.
Hard to optimize.
Very hard. Current methods are either expensive, like the lottery ticket hypothesis needing lots of pruning and retraining,
Yeah.
or they rely on highly hand-tuned heuristics for evolving sparsity. These can be brittle, hard to generalize, time-consuming.
Okay, and the third criterion.
And finally, number 3 is practical efficiency, beyond the theory.
Needs to work in the real world.
Exactly. The parameterization must support practically efficient algorithms for both training and inference.
Speed and memory.
Real-world speed and memory usage that makes them viable for deployment, moving from theoretical possibility to concrete applicability.
Right.
So, to summarize, the paper meticulously points out that, astonishingly, currently, no single class of structured linear maps satisfies all 3 criteria simultaneously.
Wow. A clear gap.
A stark reality. And this sets the perfect stage for the profound gap that Kaleidoscope matrices aim to fill, a compelling argument for a novel solution.
Okay, so that sets the stage perfectly. A huge challenge. Now, for the exciting part, how do Kaleidoscope matrices, K-matrices, actually solve this? What's the core idea?
The core idea behind K-matrices is, well, truly brilliant in its simplicity, yet incredibly powerful.
Okay.
The fundamental concept is representing linear maps as products of sparse matrices with specific predefined sparsity patterns.
Predefined patterns, that's the key.
That's the critical innovation. By fixing the pattern of sparsity and only learning the values within those patterns, they directly overcome the differentiability problem.
Avoids the discrete search.
Exactly. While retaining the high expressiveness and efficiency that structured representations demand, it's sort of the best of both worlds.
Yeah, ever. And the paper mentions a specific building block, butterfly matrices.
Yes.
What's their significance here? What makes them special?
Butterfly matrices are absolutely crucial. Their structure is fascinating because it directly encodes that recursive divide-and-conquer strategy.
Like the FFT.
Precisely, most notably the fast Fourier transform. This isn't new. Butterfly operations have a long history in numerical linear algebra.
Decades old.
Decades, yeah. And increasingly used in machine learning, too. Their recursive, almost fractal-like structure gives K-matrices their power.
Capturing complex operations with few parameters.
Surprisingly few. And this inherent regularity also makes them practical, relatively easy to implement, as the paper shows.
Okay, for our expert listeners, let's get into the nitty-gritty, the formal definitions of these butterfly building blocks. Can you break down definitions 2.1, 2.2, and 2.3?
Certainly. Understanding these is key. The paper builds them up carefully.
Let's start with 2.1, the butterfly factor beak.
Right. Definition 2.1. Butterfly factor beak. Imagine a square K x K matrix. This beak has a specific form, D1, D2, D3, D4.
Block matrix.
A block matrix where each D1, D2, D3, D4 is a smaller K2 by K2 diagonal matrix.
Think diagonal.
That diagonal nature is key for efficiency and sparsity. K is usually a power of 2 for convenience with recursion. Think of it like a small, efficient switch.
Okay, next step, 2.2.
Definition 2.2. Butterfly factor matrix B and K. Now, larger NXN matrix. This is a block diagonal matrix.
Net of the factors.
Made of individual BK butterfly factors, each size K, strung along the main diagonal. They can be different factors.
So applying those switches in parallel across the vector.
Exactly. Parallel application across segments.
And finally, the full butterfly matrix B and K. Definition 2.3.
Definition 2.3. Butterfly matrix Bn. This is the culmination. An NXN, butterfly matrix Bn, is a product of those butterfly factor matrices.
Product, okay.
Specifically, Bn, Bn, Bnn2.
Bn's line them together.
Yes. And what's truly fascinating is its equivalent recursive definition. Bn, Bn, Bn2, 1, 0, Bn2 tupe.
The recursion again, like the FFT.
Precisely. This deep structural property is what gives them O(n) log n complexity.
It sounds very modular, recursive. You mentioned their simple regular structure makes them practical.
Precisely. This regularity and the fixed sparsity pattern are absolutely key.
Fixed pattern is crucial.
It's not random sparsity where you have to find the locations. The pattern is predefined. That's what makes it differentiable and computationally efficient. Structured by design.
So once we have these butterfly matrices, how do they form the broader kaleidoscope hierarchy, the BB hierarchy?
Yes, the kaleidoscope hierarchy, definition 2.4, is a progression of increasingly expressive matrix families built on these butterfly components.
That's okay, layer by layer.
Let's break it down. First, B, the base set. All matrices expressible as a butterfly matrix BM, the recursive structures.
Got it.
Next, BB. This is the set of matrices M formed as M equals M1, M2.
Product of a butterfly and a conjugate transpose of another.
Exactly, where M1, M2 are from B. This BB form is powerful. It can represent permutations, for instance, a key building block.
Okay.
Then, BBWP expressed as a product of W such BB matrices M equals MW, M2, M1.
W is the width, stacking them up.
Right. Increases expressiveness by stacking these blocks.
And then BBW.
BBW takes expressiveness further. An NXN matrix M expressed as M equals SES.
What are S and E?
Here, E is a larger ENXEN matrix from BDW, and S basically extracts the top left NXN corner.
E is expansion, embedding in a larger structure.
Exactly. Allows capturing even wider operations.
Just finally.
Finally, a K matrix is any matrix M belonging to BBW for some width W and expansion E. This hierarchy ensures broad coverage while keeping the nice properties.
I'm looking at figure 1 from the paper. It really helps visualize this. You see the red and blue dots.
Yeah, the fixed sparsity pattern.
The allowed non-zero entries in the BB blocks. It's structured sparsity. How critical is that fixed pattern for differentiability? What's the trade-off versus learning unstructured patterns?
Fantastic observation. That fixed pattern is absolutely critical.
Why?
Because when the pattern is fixed, learning becomes a continuous optimization problem over the non-zero values. Standard gradient descent works.
Right.
If you tried to learn the pattern itself, that's discrete, combinatorial, notoriously hard, computationally expensive for end-to-end differentiation.
So K-matrices avoid that.
Exactly. That's the core trade-off. And this structure leads to significant efficiency in space and speed.
How efficient.
Each matrix in BB has 4 law no parameters. Compare that to N2 for dense.
Logarithmic dependence. Huge reduction.
Massive for large N. And matrix vector multiplication is O, log no, achieved by multiplying with each sparse factor sequentially. Very fast.
And crucially,
for the empirical applications they show, W and E are typically small constants, like 1 or 2.
meaning
Meaning these K-matrices practically achieve ON log n parameters and ON log n runtime. Highly efficient practice, not just theory.
Okay, the architecture sounds incredibly promising for efficiency. But what about theoretical power? How expressive are they? Can they capture a wide array of transformations?
Yeah, what's the guarantee?
What's the main theoretical result that gives us confidence in their universality?
The paper's main theoretical result, Theorem 1, provides a profoundly powerful guarantee. It asks, can K-matrices represent any efficient linear map?
And the answer.
It states, let M be a Nen matrix such that multiplication of M times an arbitrary vector V can be represented as a linear arithmetic circuit with S total gates and depth D. Then M, N, M, B, B, O, O, S, N.
Whoa, okay, that's dense. Linear arithmetic circuits. Can you clarify that? And why is linking K-matrices to these circuits so significant? What's the so what here?
Right. Let's unpack linear arithmetic circuits. Think of them as a formal model for algebraic complexity. A graph.
Nodes are inputs, outputs, operations.
Exactly. Inputs, outputs, basic operations like addition, subtraction, multiplication by constants. Size is the total number of gates. Depth D is the minimum parallel steps.
Yeah.
This model captures a vast majority of efficient matrix vector multiplication algorithms like the FFT, which have low depth and size.
So the implication of Theorem 1?
Profound. It tells us if a fast algorithm exists for a linear operation, one expressible as an efficient circuit, then a K-matrix can represent it.
With near optimal complexity.
Near optimal space and time complexity. It yields an OSD log S matvec algorithm and OSD log S parameter.
So for low-depth circuits.
For matrices with low-depth circuits, log n or poly log n, common for efficient transforms, this K-matrix representation matches the best-known theoretical bounds, often up to just polylog factors.
So the so what for our listener?
Is this? It's like a theoretical Rosetta Stone for efficiency. K-matrices can learn those incredibly fast, hand-optimized algorithms automatically.
Within a differentiable framework.
Yes, bridging the gap between theoretical speed and practical learnable components. It fundamentally changes how we might optimize models, learn the structure, don't just hand-engineer it.
That's a remarkable claim.
Mm-hmm.
How do they actually prove this? What's the core intuition behind this expressiveness?
The crux of the proof hinges on an elegant intermediate result. Constructing an almost tight representation of any sparse matrix as a K-matrix.
Sparse matrices as K-matrices.
They show any NXN sparse matrix with S non-zeros is in BBOSN01.
A novel characterization.
Still a bit abstract. How does a sparse matrix looking so different from a butterfly get represented?
It comes from a clever decomposition and a powerful insight.
Okay.
Imagine a sparse matrix with S non-zeros. You can decompose it into a sum of senth-n matrices, each having at most n non-zeros.
Simplifies the problem. Right. Now here's the elegant part. A crucial lemma I.1 states, any NXN matrix with at most n non-zero entries up to permuting rows and columns is a product of 2 butterfly matrices.
Wow. So even seemingly random sparse connections can be captured?
Efficiently captured by these butterfly blocks.
Yeah, please.
Then they leverage another result. Permutation matrices are, in fact, in BB, Theorem 2.
Permutations, too. That's power.
Very. Permutations are essential. Showing they're in BB aligns with known efficient switching networks, like bean networks.
Right.
This characterization is critical. It means K-matrices can effectively trade off an extra logarithmic factor in space and time for the huge benefit of full differentiability.
All thanks to the fixed patterns.
All thanks to those fixed learnable sparsity patterns, a fundamental trade-off unlocking learnability.
So theoretically powerful learnable structure. Do they actually represent the common structured maps we use daily in ML optimally? Or is it more theoretical?
This is where theory hits practice. The paper meticulously shows K-matrices achieve optimal number of parameters in runtime compared to best-known parameterizations up to constants for a remarkably wide range of common structured linear maps used ubiquitously in ML.
Think what?
Discrete transforms, DFT, DCT, DST, Hadamard transform, cornerstones of signal processing,
Yeah.
convolution, represented efficiently by circulant matrices, which K-matrices excel at, fundamental for CNNs,
Right.
Toeplitz matrices, common in signal processing, control theory, handled efficiently, often via circulant expansion, structured matrices for kernel approximation, like HD3, vital for scaling kernel methods,
Got it.
and matrices used in compact neural network design, like fast food, AC/DC, optimized for efficiency.
Wow, that's comprehensive.
It underscores their broad applicability and proven efficiency in capturing this diverse array of established structures, a practical tool.
That's incredibly comprehensive. Can the framework be extended further? What about orthogonality for stability? Or implications for ReLU networks?
Excellent question, probing their versatility. The paper indeed introduces an extension, the orthogonal kaleidoscope hierarchy, OB.
Orthogonal.
Yes, built upon orthogonal butterfly matrices, each factor is constrained to be orthogonal.
Benefit.
Improved stability during training and inference. Orthogonal transforms preserve norms, prevent vanishing exploding gradients.
And expressiveness?
Importantly, the OBB hierarchy has the same expressiveness as the original BB hierarchy, corollary K12. Same capabilities, potentially better numerical properties.
Okay. And implications for ReLU networks?
For ReLU networks, they delve into learning theory. They prove a powerful result. Finding efficient circuits for the entire network reduces to finding efficient circuits for each weight matrix.
So if K-matrices are efficient for weights
They're efficient for the whole network, a critical theoretical bridge.
and capacity.
Furthermore, they show ReLU networks with K-matrix weights have near linear VC dimension in the number of parameters.
VC dimension, model complexity.
Right. And this matches bounds for unconstrained, dense matrices. Strong theoretical guarantees about learning capacity and sample complexity. K-matrices can learn complex functions effectively without exorbitant data, just like dense, but way more efficiently.
Theory is foundational, but now, the real world. How do K-matrices perform in practice? The paper shows several fascinating empirical validations.
Yeah, this is where it gets really compelling for practitioners.
Starting with replacing handcrafted components, this is where the rubber meets the road.
Indeed. The paper provides compelling evidence showing K-matrices can replace and even enhance components that were previously highly handcrafted.
Leading to simplification and better performance.
Both. Remarkable simplification and tangible performance improvements across diverse domains highlights their practical utility.
Let's start with speech preprocessing. TIMIT dataset, a classic benchmark. What's the traditional approach?
The traditional approach, especially using MFSC featurization, is notoriously complex, painstakingly hand-designed.
A multi-stage pipeline.
Absolutely. Each stage with its own hyperparameters, domain knowledge baked in.
Like
First, framing audio into segments. Then, dithering, adding noise, pre-emphasis, amplifying high frequencies, applying a Hamming window, FFT and power spectrum calculation, mapping to the Mel scale nonlinear transform reflecting human hearing. Finally, cepstral mean and variance normalization. You can see this intricate process in the top of Figure 2, decades of manual engineering.
And the K-matrix approach to this behemoth.
Stunningly simple by comparison. It replaces the last 6 steps dithering to normalization with a single learnable kaleidoscope layer. Input is just the raw waveform chunks.
Trained end-to-end.
Trained end-to-end with a bi-LSTM acoustic model. Let the network learn the features.
So the results. Did accuracy take a big hit from this simplification?
Fascinatingly, minimal impact. Table 1 shows, on TIMIT, the K-matrix plus LSTM got 14.6% phoneme error rate, PER.
And the traditional.
14.2% PER for MFSC plus LSTM, so only a 0.4% loss in accuracy.
Remarkable.
Makes the K-matrix approach competitive with the accuracy of standard models that use handcrafted features. Learnable structure nearly matching decades of expertise.
And compared to other raw audio approaches.
It significantly outperforms them, like SyncNet, which got 17.2% PER, shows K-matrix ability to learn efficient structure from raw data.
Any other comparisons?
Supplemental results, Table 5, show K-matrix beat other structured layers, low rank, sparse, circulant, and even dense layers for preprocessing.
And hybrid models.
A hybrid model MFSC plus a K-matrix for just the FFT step got 14.0% PER, nearly state-of-the-art, shows replacement and enhancement.
That's a profound win for simplification and automation, removing hand-tuning, streamlining pipelines, What about computer vision?
Yes, they applied them there too, replacing CNN channel shuffle in ShuffleNet for ImageNet.
ShuffleNet, the lightweight CNN.
Exactly. Designed for mobile, relies heavily on a manually designed channel shuffle permutation matrix.
Crucial for information flow between groups.
Critical. Without it, channels in different groups can't communicate effectively. Another specific hand-engineered component for efficiency.
And how did K-matrices replace this?
Instead of a fixed permutation or Hadamard transform, they used a learnable K-matrix before and after each grouped one-by-one convolution.
Trained end-to-end.
Trained end-to-end, the network learns the optimal way to shuffle or mix information.
Did it improve performance or just simplify?
Both, with significant performance gains. Table 2 and Table 6 for top 5 show striking results.
Right.
Across different network sizes, replacing fixed shuffles with learnable K-matrices gave up to 5.0% further improvement in classification accuracy on ImageNet.
Example.
A 0.25 ShuffleNet G8 jumped from 44.1% to 49.2% accuracy.
Wow. And the cost?
Achieved without hand-tuned components for mixing, with only a modest space penalty of up to 10%.
Training time.
Figure 4 shows K-matrix models converged in about the same number of training steps. Stable, efficient training demonstrates K-matrices can improve even sophisticated, handcrafted architectures. Enhancement, not just replacement.
Incredibly impressive. Simplifying pipelines, improving performance. But the paper also claims K-matrices can learn latent structure. What does that mean? How do they test it?
Yeah, this probes their versatility beyond replacing known structures. They tested this with a challenging task. Image classification on permuted CFAR10.
Permuted.
A fixed global permutation applied to every pixel in every image destroys spatial locality.
Making it impossible for standard CNNs.
Very difficult. CNNs rely on local features. Historically, only FC or RNN models tackled this. The core challenge is learning the latent permutation itself, unscrambling the image. Inherently discrete, non-differentiable.
So how does a continuous K-matrix learn a discrete permutation? The approach.
This is where the design shines. Figure 3 shows it. They use a K-matrix to represent a distribution over permutations.
Not a single permutation.
Not directly. A soft, differentiable representation designed to converge to a single permutation at the end of training.
How does it learn?
By applying samples from this distribution to the permuted images and minimizing an auxiliary smoothness-based loss.
Smoothness loss.
Encourages the reconstructed images after unpermuting to look natural, very smoothly pixel to pixel.
And the learned permutation.
Once converged, it acts as a preprocessing step for a downstream ResNet 18 CNN, restoring spatial locality. Trained end-to-end.
The impact. Did it help?
Significant impact. Table 3. Compared to baselines without permutation learning, like dense plus CNN,
Yes.
the K plus CNN approach got 9 points higher accuracy, jumped from 84.4% to an impressive 93.6%.
How close to the original unpermuted dataset?
Astonishingly, within 2 points of the accuracy on the unpermuted dataset, 94.9%. Remarkable.
Wow.
The paper emphasizes generic representations such as unstructured matrices do not have the requisite properties to fit in the pipeline, highlights the K-matrix's unique flexibility.
A powerful tool for discovering hidden structure.
Even discrete, challenging structure shows versatility beyond just mimicking known patterns.
Finally, let's talk practical efficiency. Real-world speedups. How does the theoretical ON log N translate?
Right, speeding up inference in real-world language translation.
Right.
Critical application.
What did they target?
They replace dense matrices in the decoder's linear layers of the state-of-the-art Dynamicon transformer translation model.
Already an optimized model.
Exactly. Wu et al., 2019. Already 20% faster than standard transformer. Could K-matrices push it further?
The results. Speedup versus quality trade-off.
Results in Table 4 are striking. On IWSLT14 German-English task, measured on single-threaded CPU,
Yeah.
replacing dense matrices with K-matrices yielded a 36% faster end-to-end inference speed.
36% faster.
4.9 sentence SESEC for K-matrices versus 3.6 for Dynamicon. And a 25% smaller model, 30 mayparams versus 39M.
At what cost?
Remarkably minor cost. Only a 1.0 drop in BLEU score, 34.2 versus 35.2.
So it's still high quality.
Very high quality. And the K-matrix model was over 60% faster for inference than the original transformer, while nearly matching its BLEU score from years prior. Huge efficiency gain.
What drives that speedup?
Detailed breakdown shows 55% of inference time is matrix vector multiplication. Optimizing that is key.
And their implementation.
Their efficient C++ CUDA implementation of K-matrix multiplication is about 2 times faster than the optimized implementation of dense matrix vector multiplication in the Intel MKL library.
Faster than MKL.
Impressive.
Highly tuned library, yes.
Yeah.
And figure 6 shows the K-matrix speedup over dense grows with matrix size. It's within a factor of 2-4x of specialized implementations of the FFT.
Close to FFT speed.
Approaching the speed of one of the most optimized kernels ever.
So the takeaway for listeners.
K-matrices don't just have a simple and fast O(n) log n algorithm in theory. They deliver real-world inference speed benefits and model size reductions. A profound step for deployable, efficient AI. #TAD outro.
So there you have it. This deep dive reveals Kaleidoscope matrices as a truly compelling universal solution.
Addressing a long-standing challenge.
As an expressive, efficient, and critically learnable family of matrices, fundamentally addressing the problem of manually choosing structured linear maps. Offering a flexible, powerful way to bake in structure.
Simplifying pipelines, accelerating performance.
Yeah, if we connect this to the bigger picture, the key takeaways are crystal clear and empirically validated.
Go ahead.
First, K-matrices can provably represent any structured linear map with near-optimal space and time complexity. Strong theory.
Right.
Second, empirically, they significantly reduce the need for hand engineering. We saw that in speech preprocessing, CNN channel shuffles.
Huge simplification.
Third, they can successfully capture challenging latent structure, like learning permutations in scrambled images.
Very versatile.
And critically, fourth, they consistently improve efficiency in real-world models.
Yeah.
Faster inference, smaller models, like in the transformer application.
That's a powerful set of capabilities. Opens up entirely new avenues.
Definitely.
And it leaves us with a provocative thought for you, our esteemed listener. Considering how K-matrices can adapt to and even dramatically enhance existing hand-engineered structures across diverse domains, what other complex, domain-specific data transformations or model components currently optimized through painstaking manual effort could be completely revolutionized by being made learnable through this kind of universal representation?
Where else could they simplify pipelines?
Unlock latent efficiencies, potentially push the boundaries for ultra-efficient, on-device AI or extremely low-power applications that we haven't even fully considered yet.
A lot to think about there.
We encourage you to reflect on these profound possibilities and continue your own deep dive into the fascinating and rapidly evolving world of efficient and learnable representations in machine learning.